He's a colleague of mine. He worked with me on PEM fuel cell, of course, mainly on PEM fuel cell. And he spent a lot of time working on the understanding of what are the limiting phenomena in this technology. And he's involved in projects mainly on the automotive application. So he's the right guy to talk about detailed analysis of PEM. So going beyond what we have seen on Monday. That's all. I will stay here, and the floor is yours.
Good morning, everybody. Can you hear? Yes? Okay. So, let's start. Today we continue with discussing about hydrogen fuel cells. It's 9 years I've been working on hydrogen fuel cells. I say that every year I learn a lot of new things because it's a really changing field and it's really improving in time. The idea today was to start from what you did on Monday, so to discuss the lumped model. It's very simple, the most simple model you can ever think about for fuel cells, and find the limitations of this approach. Then to introduce a new measurement, that the electrochemical impedance spectroscopy, that is a transient technique necessary to separate different physical phenomena like kinetics, charge transport, or mass transfer. And finally, I will show you, most of the lecture actually will be about the advanced description of the components, the cathode, catalyst layer, the membrane, then the gas diffusion layer, going beyond the simplified description that you have found so far. Okay, if you have any questions, please stop me anytime, but not too often, otherwise we will go longer. Okay. So, let's start from this, that is the simplified model, or lumped model that we found last time. According to this model, we have basically an equation that can be used to predict the voltage of the fuel cells based on some parameters and as a function of the current and other operating conditions. Okay. Probably you didn't write it exactly this way, but in a quite similar way, because I tried to find an explicit way to separate the different losses that we will discuss today. The first term, that is logarithmic with current, you know that it is connected with the kinetics of the oxygen reduction reaction. So the process occurring in the cathode catalyst layer where oxygen is reduced. And this process has a sluggish kinetics, and for this reason, at low current density, you observe a logarithmic behavior of the voltage with changing the current. That is due actually to this term in the equation, the so-called Tafel equation. You remember this? Okay. Then the other very simple thing is for sure the membrane ionic resistance, so the ohmic effect of the membrane, that we can express as a generical resistance of the membrane multiplying the current, that will give at any current density an ohmic loss that is linear with current. Okay? Finally, the anode, in our model, we decided to neglect the contribution of the hydrogen oxidation reaction, since this reaction occurring on platinum is very fast and generally leads almost no overpotential, no loss. So, which means that we consider the contribution of the anode just as an ideal electrode giving a positive or negative contribution depending on the concentration of hydrogen, the activity of hydrogen, and so giving an enhanced potential as an ideal electrode. The last term is in the middle, the effect of oxygen activity. That is the so-called mass transport limitations. Probably I wrote it in a different way because I introduced a new parameter, that is the limiting current. The concept of the limiting current is the fact that the mass transfer of oxygen occurring across the gas diffusion layer and whatever medium is limiting your transport resistance inside your system, basically will affect the maximum current that your system can draw. Because, you remember from mass transfer, the last equation here, you know that the current, the most trivial form, divided for F, so the flow of oxygen going through the gas diffusion layer on the catalyst layer and reacting, is equal to this transport parameter, that is the diffusion coefficient of oxygen, dividing the thickness of the GDL, multiplying the reference concentration and the difference in activity of oxygen that you have between the channel and the active layer. You see that in this equation that because of oxygen flow, oxygen flux across the gas diffusion layer, so you have a certain oxygen concentration in the channel, depending on the current, you will have a gradient of oxygen inside the gas diffusion layer, leading to a lower concentration on the catalyst layer. The limit of this trick will be when the oxygen concentration in the catalyst layer becomes zero. Okay? Since the activity cannot be lower than zero for gases, for whatever species you were talking about, this means that you have a maximum current that you can draw when the oxygen activity becomes zero on the active layer. And in this case, we call this parameter the limiting current. Okay? Okay. So, basically, actually probably in the slide that I uploaded there was this red thing missing. That is the reference concentration for sure. Basically, it means that you can write again your equation that sets a relationship between the oxygen activity you actually have on the catalyst layer and the current.
Excuse me?
Yes?
Could you please be a little slower?
Yes.
Sorry.
For sure. So, could you get this? You have this limiting current, isn't it?
No, I was not able to get the part.
Okay. Basically, you have this relationship, okay, for sure. That is the same here. Basically, when you have zero activity of oxygen on the catalyst layer, you will have a definition of a current that is the maximum current you can draw. That is this definition. Okay. Then you have a mass transfer activity. That you can write as the Tapper slope logarithmically proportional to the activity of oxygen. Then you can express the activity of oxygen as a function of this new parameter. And you will find that this strange expression that you find here is just giving you the same information you had before, expressing the activity of oxygen as a function of the limiting of this new parameter, the limiting current. Okay? This is just doing some math. The point is this. So, you know that we have this logarithmic loss that is connected to oxygen reduction reaction kinetics. At a certain point, this logarithmic trend will disappear because of mass transfer limitation. And thanks to this notation, to the mathematics that we got, we have a new parameter expressing this mass transport loss, that is the limiting current, that is actually a maximum current that your system can draw because of the activity of oxygen that you're feeding in your system. At this limiting current, the voltage will drop. And you will observe that you cannot go far beyond this limiting current during your operation. Okay? Okay. Now, since we got accustomed with this equation, basically, we can go on. And the point is this. This model is based on the concept that your system is working in a steady state. So every point in this plot is a steady state condition. You have waited a lot of time, and at the end of this waiting, you got that at this current you have a stable voltage giving exactly this value. Okay. But the problem is that you have two problems. First of all, in real application, this is not happening. In a car, you are continuously increasing the speed, decreasing the speed, and so on. So this is an indication that provides you information on the performance of the material, but it's not what is really happening in a car. The second point is that the only information that you have from experimental analysis is the black curve. So you can only measure the voltage potential of the cell as a function of the current, because you cannot measure easily the potential of a single electrode, that is the blue curve, that is the potential of the cathode, or the red curve, that is the potential of the anode, or the ohmic loss. You just measure the sum of all these losses. Okay. So this means basically that you have some troubles in distinguishing phenomena when things become complex. That's why we introduce a new measurement in order to get some insight into the physics of fuel cells and to have additional information, possibly also in real time on a vehicle, not just in laboratory, but giving you more information, detailed information of the physics beyond this curve. And this measurement, that is a transient technique, is the electrochemical impedance spectroscopy that I introduced in the latest slide. Is it okay so far? Okay. Okay. So, let's think about the dynamic operation of a fuel cell. Since fuel cells are extremely complex, there are for sure many phenomena that are occurring in real life. And what we are trying to show now is that these phenomena have a different characteristic time. So all of them typically require a certain time range in order to reach a stable condition. So, for example, you do know that ohmic phenomena are extremely fast. Okay? So, for example, in an electronic conductor, if you apply a voltage, you measure the change in current immediately. You will go in the world of less than nanoseconds. So, it is extremely fast. So, all the ohmic phenomena are extremely fast, and you can study the dynamics of ohmic phenomena almost as an immediate change affecting the performance of your fuel cell. Okay? Then, if we try to increase the typical time, we observe that there are some electrochemical phenomena that are still very fast, even though slower than Ohm phenomena. For example, the charging of the double layer is another quite fast phenomena occurring in the world of microseconds, more or less. So, for example, if you are running your fuel cells at a certain voltage and you suddenly change the voltage, okay, you will observe for sure a change in current, isn't it? So, the dynamic of the change in current will have an immediate response that is due to the ohmic loss. Then we will have a kind of relaxation due to the charging of the double layer after microseconds. Then you will see the effect of the electrochemical reactions that are still slower because require also a transition of the molecules from one state to another, but still are very fast and generally occur in the world of the milliseconds. And still in here, it's not very interesting for automotive because, as you know, in automotive application, when you drive your car, probably you're not changing the speed in the millisecond world, isn't it? We are going for sure in the world of hundreds of milliseconds or seconds. That is a meaningful time for a transient in a car. in this world starts to occur also slower phenomena that are diffusion of gases. So it means that at the beginning you have a certain oxygen concentration everywhere in your system, you start to consume oxygen, so everywhere you have a drop in oxygen activity, for example, that will change in time. And this process will require from milliseconds around seconds in order to reach a steady state. Is it clear? Okay. Then, after this, there are other phenomena that are connected to the presence of liquid water, so the formation of liquid water, that are still very slow because you have condensation, evaporation, droplets going around and moving, and it's kind of a slow phenomena that may occur minutes in order to reach a steady state. The other phenomena are temperature effects that can depend also on the boundary condition of your system, the radiator on the car, for example, which will also determine the boundary condition of your system, so how long it will take to heat up or cool down your step. And finally, there is another interesting point, that is the membrane humidification that we will go through in this lecture. As you do know, the membrane performance strongly depends on how much water is inside the membrane, the so-called water content of the membrane. The change of phase between water inside the membrane and outside is generally extremely slow and can take also minutes or hours in order to be achieved a complete steady state. Okay, so the relevant point you get from this chart is that even though all these phenomena in steady state sum up and you can hardly distinguish them, if you study the dynamic of a system, you will find that there are some occurring very fast, some occurring after, and other occurring very slow. So if you study the dynamics of the system, you can distinguish all of these contributions. Okay. If you're okay with that, we introduced the electrochemical impedance spectroscopy. That is a typical lab technique that is used in order to distinguish slow phenomena and fast phenomena and have an indication of the different losses in a fuel cell. Okay, the basic of this measurement is that you start from a steady state condition. So consider, for example, here you have current applied to your cell as it changes in time. And this is the response of the cell. So at initial time, you're applying a certain steady current, IDC, DC current, and the system will respond to a voltage, DC voltage, stable, completely in steady state. Okay? At a certain point, around this steady state, you start to apply a small sinusoidal oscillation of the current, which means your current is now no more one single value, but is changing in time sinusoidally, okay? At a certain frequency. That is for sure a degree of freedom that you can set in your measurement. So the question is, what happens to the response of the fuel cell? For sure, since you are changing the current, the voltage response of the fuel cell will change, okay? And what you observe in real life is that after an initial transient in the voltage, the voltage will start to oscillate at the same frequency you are applying of the current oscillation that you are applying as an input. Okay? So you apply an oscillation, a sinusoidal oscillation of current with a certain frequency, and you get the voltage that shows an oscillation with exactly the same frequency. This is true in the linear world, okay? In a non-linear systems, for sure, this will not be always true. In order to achieve this condition, so to have exactly the same frequency oscillation of the current and the same frequency oscillation of the voltage, you need to apply a small sinusoidal oscillation, which means, I don't know, 1, 2, 3% of the steady state current that you are applying. So in this case, this oscillation would look very zoomed, okay? It should be a very small ripple around the steady state current. Okay. Now, from this thing, we want to get a measurement, a parameter, giving us information on the response, of the dynamic response of the fuel cell at this frequency that we are studying. In fact, what we can do is to define a parameter that is called the impedance, and is a complex number expressing the effect of the input, the oscillation of current, on the output, the oscillation of voltage. In fact, if you plot in time the current and the voltage one after the other, you will observe that there could be a phase shift between the two sinusoidal functions. Which means, for example, that the voltage could be very delayed with respect to the current, or the opposite, it could be that the voltage is occurring earlier than the change in current. Okay. And the information of this phase shift is related to the dynamics of the system. Because if the system is extremely fast compared to the frequency that you are applying, it will have the time to work to have exactly no phase shift between the current and the voltage. And you apply a current change that is so slow that your system can adapt every second, every step, every time step to the oscillation you are imposing, and so there is no phase shift between the voltage and the current. Okay. Instead, if there are some dynamics in your system, the system will require a transient, a shift in time, in order to compensate for all the phenomena that are occurring inside that are determining a transient. For example, protons moving on the double layer, or oxygen moving around in your system, generating oscillation of all these quantities that in the end will appear as a shift between the peak of the current and the peak of the voltage. Okay? Yes?
You said the can happen before the change in I?
Sorry? The delta V can...
The changes of I.
Yes?
Delta V can happen sooner than the changes in I?
Yes, in a general work it could happen.
We know that delta V is and the spectral change in I. How will it happen?
I mean, it could be that the peak in voltage is earlier than the peak in current, and this behavior depends whether your system is a capacitance dominant system or an inductive dominant system. Because you know that there are in electrotechnics, in basic electrical systems, you have capacitive phenomena and inductive phenomena that have a different behavior in whether the peak in voltage will occur before or after the peak in current. So in a general case, the point is that you are in a stabilized regime, exactly, and you observe that there is a phase shift possibly between your voltage and your current. Okay, whether this phase shift is positive or negative will change basically the measurement you're doing, the response. But still will be the concept that we are looking for. So it will be an information based on the dynamics of the system. Okay, so what we get is a parameter that we call the impedance, that we define as a complex number as the ratio of the oscillation of the voltage and the oscillation of the current. This means that this parameter will be characterized by a modulus, okay, an absolute value, I mean, that is the ratio between the amplitude of the voltage and the amplitude of the current. And this thing is quite clear to understand. It is, for sure the measurement will be in ohm, okay, that is voltage divided with current. And the other information that you have is how the phase shift, so the dynamics of the system is changing the peak time where the current is occurring compared to the time where the voltage is occurring, the voltage peak is occurring, okay? Okay, so I can easily perform this measurement. I start from steady state, apply a sinusoidal current, measure the output, okay? I perform the ratio of these two sinusoidal systems. For sure, a fast Fourier transform will be required in order to do this. And I get an impedance, which information is the amplitude of the voltage divided, or the voltage oscillation divided the amplitude of the current oscillation, and this thing is measured in ohm, plus a frequency, a phase shift between the two phases. Most of people generally do not consider the absolute value of impedance and the phase shift, but prefer to consider the real part and the imaginary part of this complex number, and to use some plots that are specifically used for impedance, but go for sure beyond electrochemistry. So, the concept is that you can repeat this measurement by changing the frequency, for sure. And what we will see is that at very high frequency, you will study phenomena that are occurring extremely fast, because all the slow phenomena will do not have time to respond. Instead, at low frequency, you will study the dynamics of all the phenomena, basically, especially the one characterized by the low characteristic time, for example. So the slow phenomena at slow frequency for sure will show the dynamics. Okay? Okay. What you do in this case is to perform a spectrum. So you start from a steady state, you apply a frequency, you measure the impedance, then you go back to steady state, change the frequency, obtain another value of impedance, and repeat this process, and you obtain a lot of values of impedance as a function of frequency. And the point is, how do I use this information? What people generally do is to plot impedance as a function of frequency in plots that are called the Bode plots. There are two plots, one showing the imaginary part of impedance with a sign changed because it's a capacitive phenomenon, and so as a negative imaginary impedance, and the real part of impedance, so these two parameters. And now I will try to show you how to interpret basically this measurement. So what we see is that at high frequency you will have a real value of impedance, okay, and zero imaginary part of impedance, okay? In this range, that goes around 10 kHz, you observe basically the ohmic response of your system, because you are performing your oscillation so fast that only ohmic phenomena are exalted by during this process. And your impedance, that will be real, meaning that perfectly in phase both voltage and current, will give you an information on all the ohmic phenomena of your system. Okay? And this is the real part of impedance. Then, generally, you observe some peaks in your plot. Generally, each peak is associated to a different physical phenomena. For sure, the frequency, whether this peak is occurring, will indicate what is the characteristic time of this process. Okay? For example, here in blue, you have a peak that is occurring around 10 Hz, just giving a rough value. So this is indicating that there is some typical phenomena in your system occurring around 10 Hz frequency, which means 0.1 second characteristic time. And this process, we will see, is typically connected to the kinetics of the oxygen reduction reaction. Then, if you go at lower frequency, you can find other phenomena that for sure are slower. Here you see another peak that is occurring around 1 Hz, so in the second word. This phenomena, actually, that is lower, in this case, is associated to mass transport, to oxygen transport inside the gas diffusion layer. Okay? So, you see from this plot that there is a high frequency value indicating the ohmic loss of your system, and some peaks that are connected to physical phenomena occurring inside your cell. And in this way, you could study separately, for example, the kinetics of your reaction and the mass transport of your reaction, because they are affecting features that are separated in the frequency world, okay, because they are occurring at different frequencies. For sure, if you have a system that you don't know, you will get a plot that will give you no information because you see some peaks, but how can you link a peak to a physical phenomenon? That's based on experience, and that's what I will try to show you today, how to interpret such a measure. Nevertheless, in physics, people generally prefer to use the Bode plot, but in electrochemistry, they prefer to use a different plot, that is the so-called Nyquist plot. In this case, we are getting rid of frequency, and we just plot the real part of impedance as a function of the imaginary part of impedance, always with the sign change. What you see in this case, basically, is that the peaks that you found on the imaginary part are still present in your plots. So you have a large peak here associated to a high frequency phenomenon, and here you have a smaller peak associated to a lower frequency phenomenon. Okay? You still have these peaks. Since they are more visible, in this case a lot of people prefer to use the Nyquist plot, but basically the information is exactly the same. In this course, I would prefer to use the Nyquist plot because it's just one, so it takes less space on the slide. But for sure, you can use all of them, and the concept will not change. Now, the point is that we have two relevant limits in the spectrum in the Nyquist plot. There are the 2 points where the spectrum goes on the real axis. When the spectrum goes on the real axis, which means the imaginary part is 0, what happens is there is no frequency shift, no shift between the current signal and the voltage signal. So the process is occurring exactly with the same, with no shift between the current peak and the voltage peak. This is typical at high frequency resistance of ohmic phenomena. So this is the high frequency limit indicating the ohmic loss of your system. What happens instead at low frequency is that you're performing a sinusoidal oscillation that is so slow basically that you're going through a real steady state condition. So you're changing the current and the system has a lot of time to respond, so it goes exactly to a steady state condition. So there is no more phase shift between the current and the voltage peak. And in this case, you get no imaginary part, only a real value. And this real value is the derivative of the polarization curve. Because, if we go back to our previous slide, you have a polarization curve. What you're doing in this case is exactly moving so slow that your system can exactly adapt and move just on the polarization curve, because there is no dynamics, and you're moving around a steady state condition. And you're just performing, when you're measuring the impedance, the relation between the voltage change of this curve divided the current change that you are imposing. So basically this is exactly the slope of the polarization curve in the point where you did your measurement. Okay? So, when you look at the spectrum, what you understand in this case, for example, is that your system has this value of ohmic loss, ohmic resistance, shows 2 major phenomena occurring inside your system, because there are 2 peaks quite separated, and still has a value of low frequency resistance that is basically the slope of the polarization curve and is given by this value. Okay, these are the 4 major information that you get from an EIS measurement, an impedance spectroscopy. For sure, there is a lot of mathematics behind. There are some slides on the BIP page of this course where you can have also all the discussion on the mathematical, how to obtain basically all of this information from a mathematical point of view. Okay, now let's go back to our lumped model, our simplified model. Okay, so we know, for example, we want to understand how to use impedance spectroscopy. And the question is, let's in an imaginary experiment to perform an impedance spectroscopy at low current density, where the red star is present. Okay. How will our spectrum look like? And the answer is here in the plot. In this case, basically, in our lumped and simplified model, there are two major phenomena that are determining the performance of your cell. One is the catalyst activation, so basically the kinetics of the oxygen reduction reaction. The other one is the ohmic phenomena that are expressed on the green curve. Okay? And exactly that's what you find in your spectrum. So, the high frequency limit of the impedance will be directly proportional to the ohmic loss of your system, which means substantially the membrane ohmic loss that you have. That is the most relevant ohmic phenomenon occurring in our, the only ohmic phenomenon occurring in our lumped model. We said charge transport across the membrane is extremely fast. At high frequency, I can detect it by measuring this limit, the high frequency limit, that is called high frequency resistance. Okay, and is the membrane ohmic resistance. Then, the other major phenomena that we observed is the oxygen reduction reaction that will generate a major feature, like this kind of loop, that will be actually an indication of how good the kinetics is in your fuel cell. And the idea is that there is the diameter of this element is a resistance, because we are measuring in ohm, and this resistance is called the charge transfer resistance. It is proportional on the slope of this loss, of this kinetic loss occurring in your system. Which means the bigger the circle, the worse the kinetics of your reaction. Okay?
Can you repeat, please, the name of the diameter?
Yes, it's the charge transfer resistance.
Okay.
Linked to oxygen reduction reaction kinetics. Okay. There is an analytic expression in our simplified model for the charge transfer resistance. Okay? That is obtained as the ratio between the tuple slope and the current density. So you see that is strongly dependent on the tuple slope, so the kinetics of your reaction. Where does this value come from? This value comes from the fact that we said the low frequency limit is the derivative of the polarization curve, which means if I perform the derivative of this equation with respect to current, so derivative of delta V with respect to J, actually I will find that the first term is exactly the tuple slope divided the current density. That is the slope of this specific loss associated to oxygen reduction reaction. Okay? For the same reason that is very easy to understand, the green part, the derivative of the green loss with current will be a constant and will be the thickness of the membrane divided the conductivity of the membrane, so the ohmic resistance, that is the green contribution in your spectrum.
Excuse me. Like you are saying, when we derivative with J, it becomes the OR kinetics part becomes
Yes.
the
we get
tuple.
B divided J.
Okay, that constant.
Constant, yes, depending on the current you are applying.
Okay.
For sure, the derivative here is negative, okay? So you have to change the sign in order to have a positive value of resistance, okay? But this is just a matter of sign. For sure, you will get that. So, at low current density, we have two major phenomena, ohmic losses and oxygen reduction reaction kinetics, and you have two features in your spectrum, the high frequency resistance and this big loop, indicating that there is a kinetics reaction in your system having a resistance that is proportional to the diameter of your spectrum. Okay? Okay. What happens instead at high current? At high current, in your lumped model, you have an additional loss that is connected to the transport of oxygen inside the gas diffusion layer. So basically, if you move where the red star is now, so close to this limiting current, where the voltage is going down because of oxygen transport losses, you will find in your spectrum there is an additional feature occurring at lower frequency. This feature, that is here indicated as the blue dashed line, is associated to oxygen transport resistance. Okay? So when you perform an impedance spectrum at high current density, you will find what we saw before. So high frequency limit, indicating the membrane loss, a first loop, indicating how good is the kinetics in your system, in your oxygen reduction reaction, and finally you will find a large one at lower frequency that is a proxy of the mass transfer resistance of your system. This additional resistance occurring in your system we will call the mass transport impedance or mass transport resistance of your system. This is something that is measured always in ohm and is the diameter of this circle. And you can find the value of this resistance performing again the derivative of the voltage with respect to current in your model. And what you will find is this very simplified expression, and this resistance, so the diameter of this feature, is proportional to the Taper slope divided by the difference between the limiting current and the current density at which you are running your system. Okay? That's why I introduced the limiting current, because this expression becomes quite easy to handle. The point is this. So, if you are far from the limiting current, okay, you are at low current, J lim minus J will be very large, so this resistance will be negligible. Okay? That's why in the previous case, where we had a low current density, we could say that this feature is basically vanishing. It's no more present because it is very small, so negligible in our losses. That makes sense, because at low current density we don't care for mass transport inside the gas diffusion layer. Instead, at high current density, it becomes dominant in our spectrum. And what we see is that we can do, performing impedance spectroscopy, distinguish ohmic phenomena, kinetics of the reaction, and mass transfer phenomena. This is a very powerful technique, because it means that while your car is running, you can perform this measurement and just check whether you have problem with the current, you have problem with the transport in your system. So it is very important tool for diagnostics of real system of real systems and how they operate. Okay? Okay. Now, the point is that what we want to say now is that the lumped model has a lot of limitations. Because in fact, if we get some experimental data, like the one that we use here in the plot, so the circles are experimental data obtained on a certain material, here you have a polarization curve, and then you try to fit your model, for example. And what you see is that at low current density, you can have a good consistency with your model. And then if you try to simulate the impedance spectrum and compare with the experimental spectrum, you still see that you can find some consistency, because you have a major feature, circular feature, that basically you could reproduce with your model, okay? But still you see that in this part, that is the high frequency part, still there are some differences between the model and the experiment, okay? This is the first thing that suggests us that still our model is too simple to represent a real fuel cell. But what is even more important is that if you go at high current density and you try to reproduce the limiting current with your model, you still will find that there is a very large difference between the model and the experiments in the polarization curve. And if you try to simulate the impedance spectrum, you see that it is completely different. This is happening at 1 amp per square centimeter. Okay? So for sure this lumped model is very interesting, but then if you have to use it in real world, you need to go beyond this model in order to represent additional phenomena that are occurring in your fuel cells that in this very simplified model have been neglected. Okay? Okay, so let's start making things more complex. So, what did we neglect? That's the first point. What we actually neglect was some transport phenomena occurring in a real fuel cell. That is not a lumped phenomena, so you do not have a single parameter expressing a loss in your system, but you have a distribution of properties. So the potential is not uniform in the cell. Okay? So we have to consider transport phenomena. In particular, we have to consider mass transfer in porous media in the gas phase, since we consider this only in the gas diffusion layer. But mass transfer is occurring also in the catalyst layer, for example. Okay? So we have to include mass transfer in other media. Then we have a charge transport in our system, because we consider, for example, ion transport inside the membrane. But we are neglecting ion transport in the other media, in particular in the catalyst layer also. You have transport of ions because the platinum must be connected to the membrane. And for this reason, as you remember from the last lecture, you're putting ionomer inside the catalyst layer in order to have this contact between the platinum and the membrane phase. And also you have heat transfer. So the temperature is not uniform for sure, but where you have an electrochemical reaction, you are producing heat, and for this reason, locally the temperature will be higher. So once you consider all of these transfer phenomena, you get a better consistency between your model and the reality, basically, and the experiment. Okay. In order to analyze these, you need equations. So conservation equations, the mass conservation, charge conservation, energy conservation. But this is something we will see in the next lecture. Actually, will be lecture 8. Typo. Then we have to combine this conservation equation with phenomenological equations, like for example Fick's law, Ohm's law, and so on. And you will have a closed system of the equation that you can solve in the most general case. Today we are not going to talk about equations, but we're going to talk about physics. Okay, so now consider that behind this you need to include more equations in your system. And what we try to do now is to say, okay, let's review all of our components one by one, going beyond this approximation of having a kind of uniform or simplified operation or lumped condition in your model. Is it okay so far? Do you have questions? Okay. So let's start with the cathode catalyst layer. And at a certain point, I guess, we're gonna have a break also. At what time do you usually have break?
No.
Sorry? Now is no, come on. Wait a couple of slides, just one slide at least. Okay. Okay. No, I mean, okay. We still have time. Now, so let's go through the cathode catalyst layer. This is my own drawing of how the cathode catalyst layer may look like, and I'm sorry if it does not fit with your imagination. So on the left side you have a membrane, okay, this thing here, and from the membrane hydrogen ions are coming, okay, because they are a reactant in the oxygen reaction.
In between.
Then you have ionomer dispersed inside your catalyst layer, that is this blue spaghetti going all around. Inside of it, you have your platinum that is dispersed as nanoparticles, these black dots covering your spheres. And you have carbon support. The carbon, there are these larger spheres, because in your system you are depositing platinum nanoparticle over a support. Generally, this support is carbon, some kind of carbon, okay? So your catalyst layer, if you look at it with an electron microscopy, more or less looks like this. You see these big spheres all covered with platinum, and these ionomers, this plastic basically, all are dispersed all around. You also have another very relevant ingredient, that is the porosity. So this structure must be porous because one of your reactants is oxygen, and oxygen must go through this catalyst layer. Okay? And also, you must have electrical contacts. So electrons that are coming from the GDL side, so from the external circuit, will have to go into the catalyst layer and have a transport across all the carbon structure that will guarantee the electron can move freely around your catalyst layer. So what we assumed in our lumped model is that the ionic potential is constant across the catalyst layer. So we said, when we move hydrogen ions across the catalyst layer, it is giving you no Ohm loss, because the potential of the blue phase, we consider it constant across the catalyst layer. In the membrane, no, remember, in the membrane you said, okay, we have a potential drop because of ions moving in there. So, in a general case, we could say we also have this problem also in the catalyst layer. And the ionic potential in catalyst layer, in real world actually, is not constant. So, the first assumption, ionic potential is constant, will evolve to something more advanced, and we will consider ion transport across the catalyst layer. The other thing that we assumed was the activity of oxygen to be constant across the catalyst layer, isn't it? So we said, okay, oxygen activity is the same next to the GDL or next to the membrane. But this is not true in the general case as well, because we could consider that because of oxygen consumption occurring inside this layer, oxygen could be depleted from the GDL side to the membrane side, okay? Depending on how good is the transport of oxygen inside this catalyst layer. So if you had pores like this, for example, I guess oxygen would be uniform all over the catalyst layer. But instead, if your pores are very narrow, very small, in this case oxygen will have a hard time to go through the catalyst layer, and we can, in the general case, consider that the activity of the oxygen will no longer be constant or uniform inside the catalyst layer. Is this clear? Okay. So, the evolution of this hypothesis, for sure, is that we will have to consider gas transport inside the catalyst layer. Oxygen transport inside the catalyst layer. Finally, the last point is that oxygen reduction reaction is a very difficult reaction to study. The reaction mechanism is extremely complex and depends on some absorbed species on the surface of platinum. So, for this reason, I also will give you some hints on how the oxygen reduction reaction kinetics is occurring in a real system. And this will be the talk of the next 3 slides. Now, let's go back on how the performance looked for our cathode catalyst layer according to our lumped model, just as a reminder. When I'm considering more or less the blue continuous part, so we do not care for this dashed line that was associated to the gas diffusion layer. Do you remember? We had this limiting current that was in our lumped model associated to the gas diffusion layer. Now we care more about the blue part, so from low to intermediate current density, that according to the lumped model was going through a logarithmic law, okay, expressed by the Tafel law. And we will also have some insight into how a real impedance spectrum looks like for a real cathode catalyst layer. And I remember you that in our lumped model, we saw this morning that a typical spectrum that we could have at low current density, so in the range where we are working now, you have 2 major phenomena to consider. One is the ohmic loss, the high frequency limit, that is actually associated to the membrane. So now we are looking at the catalyst layer, we don't care for it. But what we will focus now is on this feature, this circular feature that we said is associated to the kinetics, oxygen reduction reaction kinetics in your lumped model, how it will change in introducing additional and complex phenomena in our system? Okay. So let's start from oxygen transport to the catalyst layer, because actually probably between the two phenomena is the one that is easiest to understand. So let's start from our lumped model. In this kind of simplified approach, if we look at the oxygen mole fraction, you know what is a mole fraction? Yes, for sure. Proportional to the activity, basically. And you observe what happens in the GDL and what happens in the cathode catalyst layer. According to our lumped model, we have a gradient in oxygen concentration across the GDL, and then a uniform value of concentration across the catalyst layer. Because we said, come on, we neglect oxygen transport inside this thin layer, and for this reason, we will say, okay, we have a uniform concentration of oxygen inside of it. But what happens if we remove this hypothesis? If we remove this hypothesis, we have to introduce for sure a transport parameter inside this layer. We call it as a diffusivity. So the diffusivity, in this case, of oxygen inside this cathode catalyst layer. This transport property will depend on the electrode structure. So if you have a big pole or a small pole, you can change basically the value of this diffusivity. Okay? And for example, if you had a catalyst layer with very small poles, the value of this diffusivity will decrease by a factor, for example, here of 20 or 50. And what happens in this case is that oxygen that is reacting inside this layer, being consumed, will generate actually a profile inside your catalyst layer. And you will observe a decline of the oxygen mole fraction as long as you go into this catalyst layer. Because you are consuming oxygen, oxygen has problem in transport, and so it will hardly go through the catalyst layer, and it will decline from the value you have at this interface down inside this layer. Okay? You are consuming oxygen in here. A crucial point is that for sure oxygen will not be consumed in the membrane. So the derivative of the oxygen activity must be zero next to the membrane. You will have a kind of adiabatic surface, you know, like in heat transfer. Since from here oxygen is not going into the membrane, like for example in heat transfer when you have an adiabatic wall, heat is not going into this wall, you will have in this case a minimum of this value or a zero derivative because oxygen is not going far left from the zero in our system. Okay? Okay. So, if you introduce problems in diffusion of oxygen, of transport of oxygen inside this catalyst layer, you will observe that the oxygen concentration is no more constant across your catalyst layer. And the effect of this is that for sure your local reaction rate will not be uniform. Because we said the reaction rate of oxygen reaction is proportional to the oxygen activity, isn't it? But if oxygen activity is changing across the catalyst layer, then also the reaction rate will be not uniform, no more uniform across our catalyst layer. Here you have a representation of your reaction rate. What you see here is that in our lumped model, for sure it was uniform across the layer. As we observed that the oxygen concentration in this lumped model was also uniform inside the layer. Uniform oxygen concentration, uniform reaction rate occurring in your system. Instead, if you have a decline of this oxygen concentration, you will observe that the higher the reaction rate will be found in the region next to the gas diffusion layer, where the oxygen can easily arrive. Instead, in the region next to the membrane, where the oxygen activity becomes very low, your reaction will have problems to be run. And so, because of this equation, you will find that next to the membrane, oxygen limitation will impede the reaction rate that you have in this part of the layer. Okay? Okay. For example, these simulations have been run at constant current density. So all of them have been run considering to produce 2 amp per square centimeter in our system. This means that the integral of this curve must always be the same. What is the integral of this curve across the thickness? Is the sum of all the local current that you are performing through heat. And so it's basically the whole current that is during your system. Locally, I'm doing this, I sum them all up, and what I get is the whole current density that is going in my system. So that's why all of these cubes basically have the same integral area, all of them, okay? So in order to draw 2 amp per square centimeter, starting from this reference case, when I have small pores, I have to increase the reaction rate in this region in order to have still the same overall current drawn in my experiment. Okay? Okay. Now, that's what's happening locally. But what we care now is what happens on the polarization curve. So, what happens as we consider this as an additional loss in our system? What happens and what you observe is that in this intermediate current density range, when you decrease the oxygen diffusion coefficient inside the catalyst layer, an additional loss will occur. So, you will pay this poor electrode transport property as an additional loss in your polarization curve. And what is interesting to see here is that it will happen mostly in the intermediate current density range. Okay? Instead, at low current density, no effect of this parameter will be visible, isn't it? How is it possible?
Because the request of oxygen for the reaction is enough?
Exactly, more or less, because exactly, you're right. The point is that at very low current density, in this part, all the transport phenomena are not so relevant. So you're not requested to have a lot of oxygen, okay? And for this reason, your profile of oxygen will more or less be constant and uniform across the catalyst layer. Instead, when you increase the current at a certain point, you will be required to provide a lot of oxygen to your catalyst layer, and as an effect, this will cause a progressive decline of the concentration inside your catalyst layer, meaning that you have an additional loss at intermediate current density and a deviation from your ideal electrode, which means you have to use a larger engine in your car, okay? And you have to pay more your system. We also see that this specific transport property is also affecting the limiting current, okay? So from the Lambert model, we see now that the limiting current has changed. This makes sense because all of them are related to oxygen transport inside the catalyst layer, okay? So, but this, I show you this just to indicate how complex is reality, I mean, because you are considering that this limiting current is actually not just the effect of oxygen transport inside the GDL, but the effect of oxygen transport inside all of your components, all of your system. Was this clear? Okay. In analogy with this, we can derivate, we can study what happens inside when we have ion transport limitation inside our catalyst layer. Okay? The second case here, we are no more considering our oxygen sluggish transport across the catalyst layer. We are considering now that hydrogen ion, H+, now we have to go through this catalyst layer in order to react. And as we said, we can have anomic loss inside of this catalyst layer because we have to transport hydrogen ion through it, and the charge transport generally will cause anomic loss in whatever medium you're considering. So, the question is, we start from this lumped model, as before. In this case, we had a potential drop inside the membrane that was actually, you remember, proportional to ionic resistance of the membrane. Do you remember? This was what happening in the membrane. And as we said, to have some analytical and simple expression, we said, okay, let's neglect potential losses inside the catalyst layer. So hydrogen has troubles in moving inside the membrane, but actually can move extremely fast inside the cathode catalyst layer. This was our assumption in the lumped model. But, as we said, it makes no sense to consider this hypothesis. That actually is very limiting, because in the membrane you have 100% volume occupied by the ion. Instead, in the catalyst layer, only 10%, 15% of the volume is occupied by this ion. This means that for sure ion transport inside the catalyst layer will be relevant if we have relevant transport losses inside the membrane. Okay? So, what happens in this case? In this case, just happens that the potential will drop if you consider a realistic value of sigma h, that here I wrote, that is the ionic conductivity of the catalyst layer. You know what is a conductivity, okay? Ionic conductivity. Okay, in this case, what you will find is that the potential drops inside the catalyst layer, proportionally to how bad is the ionic conductivity in it. Now, what we observe here is, as we observed before, that the derivative of the potential must be zero on the GDL side, because protons will not go inside the GDL. They will stop inside the catalyst layer, which means no flux boundary, and in mathematics this means zero derivative. Okay. So, as we said before, we can study how the reaction rate is changing across our catalyst layer. Okay, we have this definition of the reaction rate. Where is the potential inside the reaction rate? Is in delta phi. So the difference between the metal solid potential, the potential of the platinum, of the graphite, and the potential of the ionic phase, so the membrane phase inside the catalyst layer. This is an exponential dependency with a minus in front of it, which could make things quite complex. But you have to remember, this rule of thumb, that if you have an oxidation reaction, you promote the reaction by increasing this potential difference. Instead, if you have a reduction reaction, you promote, so you increase the reaction rate if you decrease this potential difference. This means if we compute this thing, this means that we have the carbon potential, for example, that is here in your system. This is Pmet. So the reaction rate will be higher where this potential difference is minimum, because we are considering a reduction. So it means that most of the reaction will occur next to the membrane, where delta P is a minimum, okay? And so this equation will give you a very high value. Instead, next to the GDL, the potential difference is high. This means that the reaction rate will be lower. Is it okay? So, if we look at this means that starting from our base case, where we have a uniform reaction rate across the catalyst layer, by introducing limitation in ion transport, we are shifting the reaction rate towards the membrane. Okay? And we have a peak in the reaction rate in the region next to the membrane, and instead, the part of your catalyst layer that is far from the membrane is not working that much, isn't it? Okay? Is it clear? Okay, this is less intuitive because oxygen for sure was proportional here. Instead, potential difference is more tricky, but still, if you reason a little bit, you will find this makes sense. Okay, finally, again, we look how do we pay this loss, additional loss inside our system. And the interesting part is that, differently from what we could expect, this nomic loss is not appearing as a linear contribution in our polarization curve. Because why this is happening? Because in the past, for the membrane, we said, okay, the membrane will give a linear ohmic contribution. Instead, the catalyst layer is not doing like this. And the reason relies exactly on this problem. The fact is that when you introduce ionic transport limitations, you will have the reaction shifting towards the catalyst layer. Towards the membrane region. So it means that this parameter is basically changing the path also of hydrogen going through the catalyst layer. Most of hydrogen will stop here, only few ions will go at the end of the catalyst layer. Because of this, there is no analytical expression for this loss that appears also in the intermediate current density range as an additional loss. Which means, as we said before, you have to have larger cells, pay more to have the same power in your application. Okay? Instead, differently from oxygen transport limitations, no effect on the limiting current is observed, and all this line will collect at low potential to the same limiting current. This makes sense because these processes, in our view, are not coupled. So ion transport is so far not much coupled with oxygen transport. Now, you may think that this is something quite simple, but the implication of these results are extremely important, because when you have to design the catalyst layer, for sure, you have to manage the property of the catalyst layer in order to avoid to have a situation where the reaction rate is not occurring in a uniform way. Otherwise, it means that the platinum you put in here, which costs exactly the same as the platinum we put in here, will not work. So you are paying for catalyst and not using it in a proper way. Okay? So it is very important. Then most of the work done on materials now consists in the optimization of the catalyst layer properties. Okay. Also, just to conclude this part, what is the effect of ion and oxygen transport limitations inside the catalyst layer when you look at the impedance spectrum? Okay? In fact, in our simplified model, we had just one major circular feature, that was this continuous line that we find in both plots, here represented in Nyquist plane. When you introduce ion transport limitations, what you observe in reality is that in the high frequency part, so in the left part of this spectrum, you will see a kind of linear behavior of this electrode that is associated to problems in ion transport inside the catalyst layer. Okay? So, if you have a very high conductivity sigma H, you will have the continuous line. If you have a very low conductivity sigma H, you will have the dashed line. And you will see in the high frequency part of this feature a deviation, a distortion, appearing as a linear branch. I go back. Let's look at the experimental data that I showed before. This was an experimental spectrum. What you see in here is exactly what we're talking about. Can you see that in this part the spectrum is behaving in a kind of linear way? Okay? So we can associate this feature to ion transport limitations inside the catalyst layer. So I could do a much better catalyst layer by resolving this problem, like for example putting more ionomer inside the catalyst layer. Okay? So you see the implication of EIS is extremely important, because from here you can get a quantitative information on how much you have to solve this problem in optimizing your material. I go back, or I go forward. Here it is. Okay. The other point is what is oxygen transport limitations? What is the effect of oxygen transport limitation on the high frequency? On the impedance spectrum. Here it is represented, and what we see instead is that we have a distortion of this circular feature in the low frequency part. So we observe a kind of a large increase of oxygen, of this charge transfer resistance of the diameter of this circle, especially with a long deformation appearing in the low frequency part, so in the right part of the spectrum. This is important because it means that if I look at the polarization curve, both phenomena had a kind of similar behavior, no, isn't it? Both of them were reducing the performance in the intermediate current density range. Instead, if I look at the EIS, I see that ion transport will cause this linear branch at high frequency, while oxygen transport will cause this deformation of the whole feature appearing here. So, when performing the optimization of the material, I can look for these specific measurements in order to have an understanding what do I have to do to improve my material. Okay? Okay. For sure, you can imagine that the reason for them having two different effects rely on the fact that the ohmic phenomena are still very fast compared to gas phase transport phenomena. So for sure, this is an ohmic phenomenon inside the catalyst layer, will occur at higher frequency compared to this, that is a gas transfer phenomenon, slower, so moving to lower frequency and so to the end of our spectrum. Does it make sense? Okay. For sure, then I will have this and probably we have a break, or we have a break after this, before this. We have a break now. Okay, we have a break.